Hello everyone, I'm here to talk about our paper, Manifold Glow. Recently, most deep learning models focus on Euclidean space, which has many benefits. And it's natural for natural images or language processing to lie in high-dimensional Euclidean space. Recently, generative models are gaining attention. GANs, VAEs are useful in image in painting or image generating, which is useful in data augmentation. Today, I will talk about extending the generative model to the manifolds, which may break some important rules of Euclidean space. There are several types of generate models. VAE encode the input X to the latent space Z with some prior distribution, Gaussian as an example. Then sample from the distribution to decode or generate the X hat. The structure here is quite simple, but it tends to generate very blur images. GANs are the competition between two networks. Generator generates fake data from Gaussian noise Z, the discriminator decides whether the input is true or fake data. If we want to extend GAN to manifold space, two networks need to be fine-tuned carefully. Recently, normalizing flow-based generative models are gaining more attention. It used the invertible blocks of network to map input data into latent Z with known prior distribution. And when generate new data, just sample from latent Z. We can calculate the log likelihood of data X using prior distribution of Z and the determinant of Jacobian matrix between Z and X is shown here. If the Jacobian is a triangular matrix, the determinant is easy to compute. GLOW is one of the most common normalizing flow-based generative model. In GLOW paper, the author introduced three types of layers whose Jacobian matrices are triangular. Even though we normally care about Euclidean data, the manifold-valued data is also important in some circumstances. When measuring connectivity of the brain, each voxel is a 3 by 3 matrices or a distribution function. Both of them lie on some manifold. On the natural images, all the images are coming from some manifold, but we treat them as the Euclidean space, since we cannot find that manifold easily. In this paper, we focus on the first setup where each voxels are a manifold-valued data. In order to extend the GLOW model to manifold-valued data, here are two important questions. What is preserved in manifold from Euclidean? And for those unpreserved, how should we modify to work on manifold? For the most deep learning model, we are talking about scalars and vectors. As the example here, in R2, if we define the origin, we can easily add vectors or multiply scalars. They all lie inside the Euclidean space. The distance here is just the norm of x2, x1. The manifold we care about is Riemannian manifold, which is smooth. The distance can be defined in Riemannian manifold. But since it's not linear globally, the addition and multiplication are not preserved. We have shown that the distance is preserved in manifold space, while the addition and multiplication are not. So how should we modify the addition and the multiplication? Riemannian manifold is equipped with tangent space at each point P that varies smoothly from point to point. Also, we can define the invertible chart map between manifold and an Euclidean space. For example, the Earth map is a chart map of S2 to R2. Thus we can define the multiplication in that simple space and inverse map it back to manifold. The group operation preserves distance on manifold. Thus it can be viewed as addition in manifold. The tilde f here is a differentiable function in Rm. The chart maps here map from manifold M to Rm. So the function f in M can be defined. The computation of the Jacobian of f, using the chain rule, is shown here. Then we can move to the building manifold GLOW part. The left is the GLOW model in Euclidean space. We can extend the blocks using the modification we showed before to build the manifold GLOW. We introduce the details of each layers inside our paper. Here, beyond pure generative model, we want to build a conditional generative model which generate data in M based on information in N. We just change the prior function in Zm to depend on Zn as in equation here. The major focus in our paper is to generate the ODF based on DTI. ODF requires longer scanning time 35 minutes than DTI 7 minutes, but contains higher angular resolution. If we can generate the meaningful ODF based on DTI, we can get a balance between scanning time and the actual group difference. This is the result from DTI to ODF. The left is the original ODF, the right is the generated ODF. It's very similar with some tiny differences. And the structure of each brane is very similar for original one and generated one. For different branes, the local structures of ODF are different. For more details, please read our paper. Thank you.